Hey everybody, welcome back. This video is about coherent scattering, one of a few ways that a photon can interact in the human body. So here's what happens. The X-ray photon enters an atom in the body. The X-ray photon energy is going to be temporarily absorbed by the entire atom. The X-ray photon energy is then immediately ejected out of the atom as a scatter photon with all of the original energy, but in a different direction. That's why it's called coherent scattering. So with this interaction, it's a photon in and a photon out. Coherent scattering is sometimes given other names, like classical scattering, unmodified scattering, elastic scattering, and Rayleigh scattering. Each of these names are used for different reasons, so just be aware that coherent scattering sometimes does go by these other names. So what are the effects of coherent scattering? As with all interactions, we need to think about three different things: the dose to the patient, the dose to bystanders like the radiographer, and the effects on image quality. Coherent scattering is good in the sense that it only influences one of these three. So let's first talk about the patient dose. Coherent scattering has no effect on the patient dose. There's no energy absorbed in the patient, there's no ionization, and therefore there's no biological harm. The photon is simply scattered and continues to travel through the patient. So what about the effect on bystanders, like the radiographer? Once again, there's no effect. The scatter photon that's created is almost always forward scatter, which means it's directed towards the image receptor and not backwards towards bystanders. Coherent scattering, unfortunately, does have a small effect on image quality, and it's not a good effect. Coherent scattering creates scatter, which therefore decreases the contrast in the image. You can think of scatter like this. When we make an X-ray exposure, the combination of photoelectric effect and transmission through the patients together creates an image that would have high contrast, that is, clearly visible differences in black and white. But coherent scatter, and really any kind of scatter, simply adds meaningless noise to the image. This noise is no longer in line with any particular part of the anatomy. It just randomly adds areas of darkness throughout the image. The result of this scatter added to the image is an overall decrease in the image contrast. The image just looks more gray. And so coherent scatter and also Compton scattering do this to the image. So when and how often does coherent scattering occur? Well, like all interactions, some amount of coherent scattering occurs with every exposure, but the most important thing with this interaction is the photon energy. Coherent scattering is most likely to occur at very, very low photon energies. So if the photon has a low energy, there's a higher probability of coherent scattering, and this results in a decrease in the image contrast. The good thing is, coherent scattering is the least likely of all interactions, which means we don't need to be concerned about it. The bigger issue is Compton scatter, which will be discussed in another lesson. So in summary, here are the key things we need to know about coherent scattering. Coherent scattering occurs when the incoming photon interacts with the entire atom. The energy of that photon is temporarily absorbed by the atom, but then that energy is immediately ejected out of the atom as a scattered photon with all of the original energy, but in a different direction. The other things that we need to know: coherent scattering occurs only at very low energies, and it's not very likely to happen. Also know that coherent scattering has no effect on the patient dose. It also has no effect on bystanders like the radiographer, and last of all, realize that coherent scattering results in a very small decrease in the image contrast.